You want maybe just to go over Lewis acid real quick, Lewis base?
Sure, yeah.
Okay, so what do you know about them?
One of them is going to be the electron donor, one of them is going to be the electron acceptor. So it's going to be the opposite of the proton. So
Yeah. The nice thing is it is strictly opposite. So where you're in Bronsted-Lowry, your acid was your proton acceptor, it's now your electron acceptor. Or no, it's your electron, yeah, it's your electron acceptor. Proton donor becomes electron acceptor. The proton acceptor becomes the electron donor. The easiest way to visualize this is with borohydride and ammonia. Have you seen that reaction yet?
borohydride? Oh, no. So,
Maybe you can point it out. Sometimes it just takes actually seeing it. Okay, this is kind of the easy one because from Bronsted we know this is a base. So if this is an acid-base reaction, we know this has to be our acid. The question is why? The reason it's our acid is because this ammonia donates its electrons to then make a bond with this boron. So this one accepts the electrons by making that bond. This one donates the electrons by making that bond.
okay.
So that's kind of your simple base example. The other way to think of Lewis acids is typically they have a positive charge on them or an unfilled octet. So boron here, 2, 4, 6, well, it doesn't have an octet, so it needs to get 2 more electrons. It needs to accept 2 more. Typical way to find a Lewis base is either through a negative charge, which means it has an unshared pair of electrons, or look for an unshared pair of electrons just on a neutral species like ammonia. And typically that's where you'll find a lot of your kind of shaky Lewis acid base, is when you have these pairs that you have to look for. So you might want to brush up on your Lewis, but typically you don't need to because there's not too many. There is one more. Lewis acid or Lewis base.
That is going to be, that really can't accept any, so is it going to be a Lewis base?
It actually can accept some. And this has to do with that organic chapter you read. These double bonds, what basically happens is, if you were to have a water here, I don't think this is an actual equation, but what can happen is these two electrons that are in this bond can go out and grab this hydrogen here, and then form a bond with that onto the carbon. Oh, wait, no. I'm thinking of this wrong. The carbon comes in, bonds to the hydrogen, and these 2 electrons will go out onto the oxygen. That is strictly an organic thing that you don't really need to worry about, but they'll throw it at you anyway. If something has a double bond, it's an acid. Just remember that.
Always, if acid double bond is an acid?
Always, 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 always. I don't think, technically there are double bonds that wouldn't do anything because they wouldn't be affected by that hydrogen transfer or the electron transfer, except in special circumstances, so they could throw that at you, but I doubt they would, because that's definitely in the territory of organics. So, yeah, otherwise just look for a positive charge. No, they need an electron pair for the acids, and then for the bases they have an unshared electron pair or negative charge. And then you'll be pretty solid. And you won't use this much because most of the acids you deal with are on the Bronsted case. They're like hydrogen chloride and hydrogen iodide, that stuff. So.
Yeah.
All right, cool.